Okay. So, so far in our course, we talked about the uh, power electronic converters. We talked about the switches. We talked about the inverters, basically, and what most focusedly. And we discussed different type of configuration and topology for inverters, how they work, how they would be like the input and output would look like, what are the challenges, what is the power quality meaning, and the THD, we talk about that. We also talk about the method for increasing the THD, increasing the power quality and limiting the THD in our output. And now we are gonna talk about the different categories of inverter before we move toward the controlling system and talk about the details of the how we could control the output of the inverter. Okay, so in this session we are gonna talk about the two type of inverter, namely voltage source inverter and current source inverter, and we are gonna kind of like get to know them, know these types, and find out what are the differences is and what is the advantage of each one is for what application voltage source is preferred, or for what application current source is a better kind of like choice. And after that, we could choose one type and focus on that, uh, and move toward the design and the discussion of the control system, which is the basically the heart of the inverter and defines the output of the inverters. Is there any question about the previous discussions? Okay, I will move forward. As we, as I mentioned uh, earlier, a few seconds ago, we could categorize the inverters to two type based on the output of the inverters. Okay, excuse me. Either we could have the voltage source inverters, okay, which basically means at the output, okay, we would have a voltage waveform, okay. Our control system is controlling the voltage waveform. Our emphasis on design is over the voltage at the output, okay, and input. Or we would have a current source inverter, which respectively changes voltage with current, like the emphasis is in current. We have to like focus on controlling the current. Also, we have like a current nature, not the nature of the input and output would be the current. Okay, I put a summary of the difference between the voltage source and current source. We are going to discuss these details in the future slides. Okay, but this this table I wanted to like point out because I wanted to like post that on post this PowerPoint on Canvas. This table is a quite informative table when you wanted to like talk about the voltage source and current source inverters. So I encourage you to like go through that table later on read very carefully and pay attention to the details and try to understand the differences. Okay, so what is the voltage source inverter? Okay, let's talk about the definition. In the voltage source inverter, basically we have as an input we have a stable DC voltage source. Okay, and when we talk about the stable DC voltage source, that means we have to the regulated DC voltage, which we normally use a capacitor at the input, okay, to regulate our voltage DC source. So normally, if you wanted to like recognize the voltage source inverters by the topology, you could basically see that on the input from on the DC part of the inverter, you always gonna see a voltage regulator, which basically is a network or like a simple capacitor or a network of capacitors. Okay. As you can see in the picture, our input is gonna be voltage, and our output also gonna be voltage. Okay. Now, the switching devices in voltage source inverters are normally MOSFETs and IGBT. So the switches that have a higher speed of the switching, okay, but known for like lower current capacity. Okay, MOSFET and IGBT had a maximum amount of current that they could conduct through them. So in voltage source, we use MOSFETs or IGBTs, meaning those device has a higher capacity for switching speed, but has lower capacity for providing current. Okay. At the output of the VSI, we typically have a semi sinusoidal, or like as you've seen in your actually, like you shouldn't be able to like see that waveform by now in your simulation, a PWM, a sinusoidal PWM, okay, with controllable frequency and amplitude. So what we have at the output is a voltage waveform created by that sinusoidal PWM that mimics a perfect sinusoidal, try to mimic a perfect sinusoidal, okay? And it's controllable for the parameters of the frequency of the output and amplitude of the output, okay? Now, the application of the voltage source are normally the renewable energy systems. Okay, so in renewable energy system like solar or like wind or like energy storages, okay, they normally used uh, voltage source inverter, okay, because they are capable of converting the DC power or DC voltage, which is normally the output of like the solars or like energy storages, okay, and have it a grid compatible kind of like AC waveform because we have control over the frequency and amplitude on the voltage. Okay. We also could use them in motor drives. Okay. One of the other application of the voltage source inverters is to drive motors. Okay. And this is based on the factors that we could have the control over the amplitude of the voltage, which if you search on the how the induction machine works, okay, or how the synchronous machine works, okay, since you have a control over frequency and amplitude of the output voltage, okay, meaning you have control over the speed and the torque provided from that motor. So you can drive the motor using the voltage source inverters, okay? Again, as we talked about that, because they work on as an input, they work with a DC voltage, okay? One of the other main application for voltage source inverters are UPS system. When you want to like have control over the energy storages, okay? As you know, the UPS system has normally like a battery or like energy storage system, okay, and try to provide an uninterrupted power using an inverter. When the grid is off, you use the battery or like the energy stored in the UPS system, converting it to the AC using the voltage source inverter and providing a stable power for your loads. Now, how about the current source inverter? What are the basics of that? As you can see from the figure, the current source inverters, okay, as you can also tell by the name, the input is a constant DC current, okay? So voltage source works with the input of voltage, current source works with the input of current, okay? And when we say we have a current source, it should immediately come to your mind, oh, sorry, that here, if you could see, pen, when we say input current, it should immediately come to your mind that we would have an inductor in the input. Why is that? Because the inductor is the component that could stabilize or regulate the current. And because it is electromagnetic, kind of like the magnetic field in inductor is playing a very important role, basically means the inductor nature of work is with current. Is that clear? Is there any question about the statement that I made? The last statement about the inductor? Anyone has any question about that? Okay, hopefully it is fully clear. So the input is DC current, okay, which provide a high power source of battery, okay? And the DC current is regulated using the inductor. Why the pen is jumping? Let's forget it. Okay. Now, because we are acting on a current, okay, the switching devices used in the current source inverters are normally thyristors or a certain type of IGBTs, okay, because they are capable of handling a high amplitude of the current, okay. In current source, because we are working in a current, our switches should be able to work with a higher current stress, okay, and they should have a more capability or capacity of conducting current. So normally, even like I could say that I mentioned the IGBT as a option for current source inverters, but in practical work, because normally the current we are gonna see about the application of the current source, they normally use thyristors, okay? Which thyristors you can find the detailed information in the reference books that I put on the canvas about the thyristors. But to sum it up and to like compare the thyristors with the FET switches and IGBTs, thyristors are not self-commutated. So you cannot turn on and off just by sending a gate signal. You need to force them, for the thyristors, you need to force them off and on. Okay, so they are not self-commutated. So you need when you're using thyristors, they are, you can say like this is like a half controllable, semi-controllable switches. Okay, so you need a redundant circuit in order to control the turn on and off of the thyristors. This is the main differences between the thyristors and IGBT. So by that being said, you might understand or you might guess what are the like the basic challenges is when you want to like have current source inverters. And we already talked about the general challenges of the voltage source inverters in previous sessions. Now, at the output, again, it could be guessed by the name of the topology, the current source inverters. At the output, they provide typically a semi-sinusoidal, or like as we said, like a PWM, sinusoidal PWM that mimics the current, the perfect sinusoidal, try to mimic the perfect sinusoidal as a current in your output, which is also controllable for frequency and amplitude of the current. Yes, Christine, do you have a question?
Yes, can you hear me?
Yeah, yeah.
Okay. So I know you said there was a DC source or the current source going in on the gates for each of those sets of FETs. Is that a different um like step input, or can that all come from one step input?
It is the topology that you see in the in the screen is a three-phase inverters. Okay, is a full bridge three-phase inverter. Okay, so each of the legs provides one of the phases. So beside the fact that they have to have 120 phase shift with each other because there is three phase. Okay, to answer your question, no, the PWM is the same as what we discussed before. The technology in the control is the same as what we discussed before. The only difference, as I mentioned, in the current source inverter is the type of the switches that we use normally in application. Okay, you can use the IGBT or MOSFET, but it would reduce the capability of the current that you can provide. Okay, if you use the MOSFET and IGBT without any change, you can provide the same signaling as you did in previous sessions and in your so far in your assignment. Okay, but in practice, current source inverter, they don't use IGBT or MOSFET normally. They use thyristors. Now, if you have a thyristor, in order to apply the PWM, okay, it's not just a single, just a simple input signal to the gate because there is not just a gate for thyristor. Thyristor could be turned on, but for turning off, you need to force them off. So for igniting, you can use your simple signal of the PWM as you did before, okay? But for turning off signal, okay, simply cutting off the gate would not be enough. You have to have another control circuit in parallel with your switches to force them to cut off the current by applying the reverse
Okay.
voltage. Did I answer your
Right.
question?
Yes, yes, that's what I was wondering because I was a little confused when you were talking about the transistors and these looked like the FETs, so I was just making sure.
Yeah. First of all, this is thyristors. They are different from transistors. Okay. But yeah, your concern is correct. The switching symbols here are, I don't think is that they are IGBT, but they are not thyristor symbols. Okay. So but the general idea is what I said. Yeah. Uh the, is there any other question about this uh concept? Perfect. Now, what are the application of the current source? Basically, based on the difference, we said current source provide current, okay, and the output is current, and they have more capability, more capacity of providing current compared to the voltage source. So it seems that one of the application could be industrial drives. Okay, when you have a high power application, meaning, and this is a parenthesis. I want to open the parenthesis. Okay. When we talk about the high power applications, okay, the rule of transferring power in power system for transmission of the power is to increase the voltage and decrease the current. So you create low loss transmission. In the load, you decrease the voltage and increase the current. Okay, for less for a smaller dimensions in your practices, because if you have a higher voltage you need you need bigger insulations. Okay, so this is the parenthesis. This is one of the hints that in power system works. The transmissions works in higher voltages, lower currents to avoid losses. The application, the loads normally works in relatively lower voltages and higher currents. So they could have the dimension wise and cost wise, they would be in more efficient kind of like design. Now, that being said, because we need to provide in high power performances, in high power application, we need to provide a relatively higher value of the current. Okay, CSIs, the current source inverters, are a better choice based on their capability for driving the industrial or like high power applications. Okay. Now, if you wanted to like use a regenerative braking, we kind of like mentioned that for like in electrical trains, okay, or elevator, when you wanted to like recover energy, okay, during your application, again, your choice, the better choice could be CSI because the nature of the recovering energy is current, not voltage. The nature of recovering energy is current, not voltage. Anyone can tell me why this statement, why I made that this is a statement like the uh, this is not about the electrical engineering, is a general physics kind of like concept. Why when you want to like recover energy like for a moving object like a train or like elevator, the input for the recovering part is current instead of voltage. I made that statement. Anyone can tell me why this statement I made that statement? What is the concept behind that? Is there any guess?
You said why the load is more current instead of voltage?
No. When you wanna to like my question is that one of the application of the CSI is regenerative braking. Okay, like for example, you have electrical train. When you wanna hit the
Right.
brake, you could put the energy, the kinetic energy of the train to the loss, or you could reuse it to charge the batteries or give back to the grid. Okay, so like some sort of like the new technology that Tesla want to work on it. Okay, like the Tesla
Oh,
vehicles, when you hit the brake, instead of trying to lost the kinetic energy of the uh, vehicle through the lens and through the brakes, they try to use it to generate some energy and like recharge the batteries.
right.
Okay,
So I'm
so
assuming
now,
it has to do with the translation of energy.
yeah, now
Can't have the same thing.
what I'm saying is that for regenerative braking, okay, the best inverter is CSI, the current source. Why? Because my statement is that because in regenerative braking, the input, that kinetic energy that we want to like prevent losing it and want to use it as a source, the nature of it is in current, not voltage. Okay? Anyone can tell me why the nature of a kinetic energy, okay, that we wanted to use, I consider it as a current, not voltage. This is my
Because
question.
it's translational. It's by time. I don't know. My
Voltage
guess.
is also voltage. We have okay. Let me explain that because I believe they would not cover that concept. It gives you quite a good intuition actually, like about the electromagnetic energy transfer. Uh, in mechanical energy, you have two type of energy. Okay, simply categorized: potential energy and kinetic energy. Kinetic energy is defined by the movement, is the energy stored, like a momentum energy stored in the moving object. Potential energy is the energy stored by the potential force applied to that energy. Okay, now let's come back to the electromagnetic kind of like field. In electromagnetic field, I believe I mentioned it twice. We normally assign electrical field to voltage, meaning electrical field provide an external force, a, a potential force for movement of the particles of energy. Okay, and we consider the magnetic energy, we represent that normally by current. Okay, which basically means the kinetic energy of those particles of energy. I don't know what's the.
So does it go back to I equals dV over, what is it, T?
Yes. Yes, kind of like you're having the right direction. Okay, so current represent magnetic field, which you can consider it as equivalent to kinetic energy. Okay, in mechanical, when you want to like visualize it, voltage represent electrical field, which you can consider it as a potential energy in mechanical engineering. If you wanted to like kind of like visualize what's happening in uh, electromagnetic field, okay, consider the energy as a particle, like a small uh, bullet of energy, a small ball, okay? And the kinetic energy and potential energy of that moving balls would be represented by electrical field and magnetic field. Is that clear? I wanted to like have for you uh, to have a kind of like a better understanding and intuition regarding the uh, what was that? Regarding the electromagnetic field. Okay, now another type of application is welding and heating. Why? Because in these application we need a higher current and we need a stable current, okay, at the output. So this is another application of the CSI. Now, I want to add something. I think I put that in somewhere in this in a slide, in the next slide, but I want to add something. Okay, let's say I want to ask actually a question. Let's say I have an inductive, okay, an inductive load. Okay, my load is an inductor. Which one, which one, VSI or CSI, you prefer to uh, uh, as a source to supply the inductive load? Anyone can have a answer to that question?
High current.
Sorry,
Current.
current source. Can you tell me why?
Inductive loads, don't they take higher current? Like their voltage is less. I don't know. I don't know.
Okay, let's redefine that. Your answer is correct, but let's redefine, kind of like look at a different perspective. What is the main characteristics of an inductor when we talk about the voltage and current?
It lags. It causes the current to lag the voltage.
It causes the current to lag the voltage. Why? Because L doesn't like sudden changes in a in a current. Do you remember that? V
Right.
was di over dt, and there is an L here. Okay? Inductor doesn't like change in a current. So if the inductor prefer the stable regulated current, the best source is CSI because CSI would provide a stable regulated current. Is that clear? So this is kind of like I want to like give you a lot of like a more perspective of what's gonna happen. Okay. Same goes for the capacitive load. Okay, if you have a capacitive load, the best option would be VSI. We don't have normally capacitive like pure capacitive load, but if we have in a special kind of like situation, voltage source inverter would be the perfect answer to the VSI because they provide a more regulated, stable voltage. Now, let's compare the general differences between the VSI and CSI. Okay, the basic difference we already know. We already talked about that. The difference between the inputs. One works with the voltage, the other works with the current. We said there is a difference that between the switching devices that they normally use. VSI normally use MOSFETs or IGBTs, okay, where when CSI normally use transistors, they use IGBTs, but practically CSI, as I mentioned, CSI normally uses transistors, okay, because of the high current capabilities, okay. Now, another part is the protection mechanism. based on the nature of their work, you also can kind of like guess that when you want to protect voltage source inverters and current source inverters, because the voltage source works with the voltage and current source works with the current, the type of protection that you use should be different. So the VSI normally incorporate over voltage protection, while CSI normally require over current protection. Okay, so uh, this seems kind of like a very simple and like very kind of like surface level uh, difference, but when you want to like actually implement the protection system, there is a huge difference between the over voltage and over current. This is not within our scope of course, but I just wanted to like mention that if you are interested in protection, very different approaches should be taken when we talk about the over voltage or over current. Okay, now another difference is commutation. I mentioned that already because CSIs normally use tristor type, kind of like switches, okay, they need an external commutation circuit so you could turn off the switches. In voltage source, you use MOSFETs and IGBT. The turn on and off is simply by sending a signal to the gate. Okay, if you turn off the signal or reverse the signal to the gate, the switch in the voltage source, the MOSFET and IGBT would turn off. But tristor, there is no turn off signal in tristor. You can turn it on by sending a signal, but you cannot turn it off by signal. You have to force it like a diode. You have to force it, put it in a reverse bias so you can turn it off. So that means you need another circuit, an external circuit, which basically add a complexity to your control system. Okay. Uh, Let me see the chats. Yeah, Maddie, your answers are correct. Sorry, I missed your answers. Thank you, thank you. Your answer is correct in the chat. Yeah. Okay. Now, other comparing between the VSI and CSI from performance aspect. Again, output characteristics. VSI provide a voltage at the output, a controllable voltage at the output. CSI provide a controllable current at the output. Okay. Another difference is from the harmonic component. Okay, a harmonic that they introduce at their terminals to the output, to their output terminals. Okay, voltage source normally have a high current harmonics. You already seen what's going to happen when you simulate a voltage source using supplying a resistance as a load. The current would be also an SPWM having a huge load of harmonics in it. So they normally require, the VSI normally require a passive filter for controlling the current harmonics that you put into the load or inject to the load. On the other hand, the current source have a high voltage harmonic. Okay, high voltage harmonic cannot be simply regulated using the passive filters because passive filters works with the Ohm law. You remember that when we talk about the passive filters, we said the passive filters work with the Ohm law. They use the dependency of impedances of inductance and impedance of a capacitance to the frequency, so they could decide which harmonic should be sent to the ground and which harmonic should be which frequency should be sent to the output. Okay, and like a low pass filter kind of idea. We talked about that previously in the filter session. So that process basically means, because it uses Ohm law, okay, basically means the filter itself do not work on a voltage. It works to reduce the harmonics on a current. Voltage is an input. It uses the Ohm law, so the output is current. Okay, so uh, therefore, for voltage source inverters, you need to have passive filters in order to damp or mitigate the harmonics in your current's output at output. Now, CSI would introduce higher voltage harmonics because there is no control over the voltage in the control system of CSI. Okay, we are gonna talk about that later on a little bit. So, in order to manage the high voltage harmonic at the output, you need more advanced filtering technique, like active filtering technique. Now, from the efficiency perspective, VSI VSI have lower switching losses because it has lower current conductance. Okay, but CSI has higher switching or conductance losses because continuous current flow through the inductors and the switches. So efficiency wise, VSI has a higher efficiency than CSI, has lower losses, lower power losses than CSI. And as we already mentioned, the control complexity, VSI has much easier control system because it's self-commutated, but CSI require a more complex, basically external commutation for control system. Now, so far we only talked about the general aspect of the VSI and CSI, or if I wanted to like put it in another terminology, we discuss the differences when we talk about the steady state performance. Okay. Now, what happens in a dynamic performance? Because not always we have a steady state situation. We would see some like dynamic changes in our parameters. Now, what is the dynamic response of the voltage source inverter should be? What is the characteristic of that? In the voltage source inverters, okay, the factor that influence how the inverter would respond to a sudden change, okay, how it would behave when you change something at the output, okay, it depends on the switching speed, control algorithm, and load type, okay. These factors defines how the behavior of the voltage source inverter to the sudden changes and how much harmonic that change, the response to that change could create at a short time to our and injected to our system. Now, when you have a resistive load, VSI performs a very good job, okay, because it has a stable voltage. The transient would be minimal. Any change in a load would be answered perfectly well, very smoothly. So only power quality issue would rise because we use PWM switching, okay, which we cannot avoid. This is how the inverters work, okay? When you have an inductive load, okay, VSI exhibits transient oscillation. We talked about that a little bit a few minutes ago. Inductive doesn't like changing a current. And the voltage across the inductor, if you change the load, meaning change the current, the voltage, a sudden change, that voltage across the inductor was L di over dt. Okay? A sudden change in a load would create a spike for the voltage because di dt would be a high number, so the voltage would increase rapidly or a spike very kind of like with a high value. So in resistive load, in inductive load, the voltage source, because doesn't have control over the current, over the output current, it exhibits more oscillation and more voltage stress when it want to respond to the dynamic change in the load. Okay, so that being said, when you use the voltage source inverters, you need to consider those responses and you need to have a technique, you need to implement a technique to control those problems, those spikes, oscillations that would happen because of the changes. Now, if you have a nonlinear load, because nonlinear loads, okay, normally introduce harmonic and add kind of like harmonic to already existing harmonic at the output of the voltage source, okay, VSI needs again a better kind of like filtering technique and it's more sensitive to that harmonic component. How about the CSI? What would be the dynamic response of the CSI? In CSI, the factors that affect the behavior of the inverters in responding to a sudden change, okay, is the factors are the control algorithm, the switching device efficiency, okay, not the switching device speed. The switching device efficiency, meaning the power loss in switching devices, and the load type. So the main difference, VSI, the speed of switching is important. CSI, the efficiency of the switches are important. Okay? Now, when you have a resistive load for a CSI, again, like the VSI, it would exhibit a very good adjustment. It has an stable current. You change the load, it would answer to that, and no problem for responding to the dynamic of a resistive load. When it comes to inductive load, as we discussed, it is much well suited, much better to answer the inductive load because it would regulate the current and minimize the oscillation due to the changes of the current. So the stress of the uh, dynamic change in a inductive load when you use the CSI is much lower than when you use uh, voltage source. In nonlinear load, they could introduce the voltage distortion as it is kind of like uh, predicted because they are nonlinear loads. Okay, and same as VSI, CSI also needs advanced filtering techniques to answer or mitigate the distortion caused by the nonlinear loads. Is there any question about the dynamic response so far? Do you have any question about that discussion or any point you want more clarification? No? Okay. So let's move on. What are the challenges and limitation of those inverters? Okay. When you want to work with a VSI, okay, the challenges that you would face is over voltage. So you need over voltage protection. Why the challenge is over voltage protection? We already discussed that in dynamic response. Okay. Because VSI cannot handle the inductive load, and you normally in power system have inductive load, okay, you need to deal with those spikes, those voltage spikes caused by that LDIDT. So you need over voltage protection in order to guard your components. So your component would not face a high stress of voltage and would not kind of like break down the insulation in them. Okay, so this is the story behind why we need a over voltage protection in VSIs. We already talked about the harmonic distortion. We need a, uh kind of like a advanced filtering technique at our output. And another challenge, where is my pointer? Another challenge, as we mentioned early in the course, is the thermal management, because VSI, as we talked about it, has a higher switching rate, switch faster than CSI. They would face higher switching loss. Okay, so they need the thermal management. Okay, what about the CSI challenge? The challenge in CSI first is the overcurrent protection. If you have any kind of capacitive load or you have a short circuit because they are current source and they have to answer the current to their terminal. If you have a capacitor or a short circuit at your terminal, there will be a rush of a current through the CSI. That means you need to have an overcurrent protection in order to control or protect your component uh, uh, over the uh, overcurrent. Okay, and yes, yeah, there is a very good example when we talk about the power sources in lab that you had, like in C lab or E lab. Okay, there is gonna when you put it in a CC mode, a current mode, the overcurrent protection would kicks in. Okay, so this is kind of like one of the situation. Okay, yeah, and another challenge we already kind of like mentioned that I wanted to like insist on that because it's very important when you want to talk about the CSI, and it's the commutation. Remember, in CSI you need more control, more complex control system. You need to have a PWM to ignite the switch and an external commutation circuit to turn off the switch. Okay. Another challenge is that because the CSI works with current, that means they have inductor in both input in the DC part and in both in the output in the AC part. Okay. And because of that, they normally have bulky components and they are larger in size. Okay. Again, for the larger in size, not just because of the component, because CSI uses the different type of switches with a higher current capacity. That would also add kind of like a challenge over the dimension of the inverters and the size of the components. Now, let's put everything together. Let's talk about the uh, comparison of VSI and CSI. VSI has a good dynamic performance because it doesn't have any inductor in the DC link. In CSI, the current cannot instantaneously change. Okay, so it reduces the system dynamic performance. We already talked about that. The CSI inherently try to regulate current, so it will not even allow, or it cannot allow the sudden changes in current. Okay, and the protection at the supply side normally happen in the VSI, not at the load side. So for if you want to use the VSI in your system, you need to have a protection over your load if you want, because the protection system in VSI tries to protect the supply side, the DC side and the switches, not the output. In CSI, the protection protects both sides. It's an overcurrent load, so it protects both sides, both supply and the load side. Okay. VSI has poorer reliability, okay, and needs uh, anti-parallel diodes to protect about to enhance that situation. CSI has higher reliability, okay, and doesn't need the anti-parallel diodes. But you need to not forget that they need a external commutation circuit, which basically kind of like you could say it kind of like even up these benefits. Okay, so VSI has higher frequencies of switching. Okay, CSI works with lower, has higher efficiencies. VSI has lower efficiency. VSI can use a wide range of the control method. Okay, and normally uses like the SPWM or SVM, as we talk about. Current source also should use different type of control algorithm, like selective harmonic elimination, selective harmonic elimination algorithm, or uh, oh, what was the other control method for this? Oh, I just forgot the control method. I think I mentioned it somewhere, but okay, I will tell you when I uh remember that this is two type of general method for CSI. This is SPWM and SVM. This is selective harmonic elimination and another type I uh I don't know why it ran away from my thought. Christine, do you have any question?
Yes. Sorry, I realized that I just waved instead of raised my hand earlier.
Yeah.
So if you're dealing with a circuit that requires um that's just a like a DC component circuit as we had in lab, is that why we didn't use the constant current whenever we used the motors? Was because it would create a lot of voltage transients in the circuit?
Uh, can you explain more? I can't follow your question.
I was curious why we didn't use the constant current mode when we were dealing with the motors. So I know they have to have a higher current to start. And that's kind of my other question on this with the current source mode. Um, I'm just wondering if you use constant current mode with an inductive motor, you're gonna get a lot of voltage transients that'll end up in the circuit, or is that only if you don't ground the motor?
It will end up in a lot of transient.
Okay.
Okay, so
And
it
then,
will because it's your the nature of your load is uh uh inductive,
huh,
and any sudden change, which you will have sudden change, okay, especially when you want to like start the motor in the period of starting the motor, okay, you will have that sudden change. It would create an unbelievably high voltage stress because the IDT is gonna be very high value, is
mhm,
gonna be a very high value of voltage stress over your circuit.
right. So how does the CSI mitigate that starting difference in the current for an inductive motor?
The CSI would regulate the current, okay? Inherently, it would not allow the change in the current. So
Right.
when you want to drive an inductive load like a motor with a CSI, okay? Like if you use VSI, you could easily like very fastly start the motor and put it in the desired system in the desired speed. Okay, but in CSI, it would not allow the motor to drain sudden current from the source. Okay, so you need more time to get to the desired point of working, but CSI inherently controls the gradual increase of the current, so it would avoid any kind of like transient voltage spikes you happening in the system. Did I answer your
So it would
question?
not really, kind of. So it would slowly start the motor, or we would have to use something else to start the motor and then switch to CSI.
No, it would not allow sudden change. When you have like a motor and you connect it to a source, okay, at the first step, it would the source would see a short circuit, okay, because the load is not energized. So there is a
Right.
huge load, okay. So it wanted to like by huge load, I mean huge current draining from the source, okay. That huge current drain means in time domain means very high DIDT.
Right.
Okay. But if you connect it to the CSI, because of the control technology in the CSI, we are going to talk about the control system later in the session. Because of the control algorithm of CSI do not allow draining a huge amount of current. So it
Right.
would limit the current. Ergo, it would limit the higher spikes.
Right. No, I'm sorry. You keep repeating the same thing, but it's not what I'm asking. I know it doesn't allow it. We've covered that. That's why I
Yeah.
have the question. So, how would the motor start then if it doesn't allow that spike? How would we start it with the CSI source, is what I'm asking.
It takes more time. It's an induction
So,
machine.
it would just be
Okay.
a gradual start then.
It's just a gradual start. Yeah.
Okay. Okay.
Yeah. Did I answer your question?
Yes.
Yeah. Okay.
Thank you.
Perfect. Okay. So this is basically our conclusion and talking about the voltage, so two category of voltage source inverters and current source inverters. Okay. And I also, again, I summarize the differences in the last slide. There's a table, and in the first slide also I had a table. I really encourage you to like look into that. In the next session, now that we talk about the categories, in the next session, we are gonna choose one type of inverter, which we are gonna choose the voltage source inverter, okay? And we are gonna talk about, okay, now we have the topology. We know what kind of inverter we want to have, like a voltage source with, like, for example, like a full bridge topology. Now, how we can control the parameters at the terminal by adjusting the control parameters that we had and we discussed earlier and when we talk about the SPWM. Any question about the discussion that we have? No? Okay, so this is for today. I hope you will have Great rest of the day. Stay safe and be careful because it's gonna be like tonight and especially tomorrow. Tonight is gonna be, they said is gonna be a snow. Tomorrow is not gonna be much better. The snow is gonna end, but it's not gonna be much better. So try to stay safe and have a good rest of the week. Thank you.
You
Thank you,
too. Thank you.
Professor.